And here we go. Okay, this is type 3 of nomenclature. Yesterday we were learning about the nomenclature of compounds, not necessarily acid or base or anything, just inorganic chemical compounds, of naming a nomenclature of inorganic compounds, right? So in that number 3, there are 3 categories that we can find or name it. And this thing falls on the number 3 when 2 non-metals or metalloids join together to form a compound. So the non-metal that occurs on the extreme left on the periodic table will be named first, and the rest will be followed. And of course we have to use the prefixes like bi, di, tri, penta, tetra, penta, on all those things. So first of all, I mean here hydrogen iodide, okay, nitrogen trifluoride, dinitrogen tetrachloride, silicon dioxide. So here it will be all those things. I mean the prefixes will be named in this case. All right, so now we move on to the acids. Those are simple acids. We will talk about it. And those simple acids, compounds that are able, I mean, there are different definition for acid, right? We already have known that Arrhenius definition of acid, and then Lewis definition of acid. So there are Bronsted-Lowry. So in a simple sense, we will read or we'll study more about it, acid and base, in the weeks to come. But in a simple way, the acids are those that can donate a hydrogen ion or proton. Proton is the hydrogen plus, right? Because in a hydrogen atom there is no neutron. So when there is proton, means electron goes away from that atom, so it becomes positively charged, and that's why it's called proton. So on hydrogen ion, when they, I mean, the compounds or chemicals that can donate one hydrogen ion, and the anion does not have any oxygen, that will be a simple acid. Okay, so when there is oxygen, that falls in the different category, that oxo acids. We will be going there in a bit. So simple acids will be no oxygen, and there will be and it will be able to donate a hydrogen. It doesn't matter whether it is a strong acid or not strong or weak acid, but it will be an acid. The name, the change of the anion from ide to ic acid will be named. When we name them, it will be ic acid, IC will be added before we add the term acid there. Before we add the acid term there, ic will follow. The examples for them are HF, hydrofluoric acid. Okay, hydrofluoric acid. Then hydrosulfuric acid, hydrocyanic acid. Okay, so this thing we have seen there is no oxygen, and this is able to, I mean, when it dissociates in aqueous medium, it is able to donate a hydrogen ion, right? Of course, there will be an ion there too, but hydrogen ion can be donated from here. So in aqueous medium, that means in presence of water, that is in aqueous medium. Okay, so all right, so this is the name of the acid, hydrofluoric acid, because it was a fluoride, sulfide, and cyanide, right? So from that fluoride, it becomes fluoric acid. From sulfide, it is sulfuric acid, and from cyanide is cyanic acid. Another thing, many of the times I'm sure that we have heard or we have seen this type of thing, that when it is we call hydrogen fluoride, right? How about the names hydrogen fluoride, hydrogen sulfide, and hydrogen cyanide in this? Why is it not, I mean, what is the difference? All the same thing, HF, hydrogen sulfide and hydrosulfuric acid. So this is the same thing. There is nothing changed. There are hydrogen and fluorine there. Only the thing is when they are in acid, that is aqueous medium, we will call ic acid, but these are gas. So they are gas, and these are, that is why there is, I mean, it is not in aqueous medium. They have not formed acid. That means in that gaseous form, they are not able to give you a proton. So they are not acid technically. So this is why we call it as hydrogen fluoride, sulfide, and hydrogen cyanide in the gaseous medium. Okay, so name of the simple acids are, we have seen earlier, hydrogen fluoride, hydrogen chloride, hydrochloric acid, and in the gaseous medium it will be hydrogen chloride, hydrogen bromide, if they are gas, not acid. But when they are acid, hydrobromic acid, iodic acid, cyanic acid, all these things. Oxo acids. That acids, they are able to deliver hydrogen ion. Of course, this is the basic thing for an acid, and it also contains an oxygen atom in that molecule. All right. And there is something changes with the naming, that when if the anion ends with ate, ate, then it will be ic acid, like it was carbonate, right? The anion is here. This is the anion part. Hydrogen is not anion because it is always positive. These are the anion, and all of them, the name ends with ate: carbonate, nitrate, sulfate, phosphate. So, and that is why it will be ic acid. So carbonic acid, all right, and nitric acid, sulfuric acid, phosphoric acid. So when the anion, remember the anion, when the anion name ends with ate, the acid will be ic acid. The same first part of the anion will be taken, and the second part, ate, will change to ic. All right. So now acid with anion, oxo acids, that we already know that acids that contain oxygen, and if the anion ends with ite, it will be as acid. Nitrous, there is a difference, nitric and nitrous, right? When there is 3, it is nitric. When there is 2, it is nitrous. So from that nitrous, it becomes nitrite. Okay, when it is 3, nitrate. When it is 2, it is nitrite, and since it is nitrite, it becomes nitrous acid. So it becomes a nitrous acid. It is a sulfite ion, so it becomes a hydrogen sulfurous acid, and so on. Phosphorite becomes phosphorus acid. There is another category that you can pour for this oxo acid, that is par, okay, ic acid. And this par-ic acid is for this hypochlorous and hypochlorite, hypochloric, chlorous acid. It is this par and ic are taken because the difference of their oxygen atom in them. oxygen, number of oxygen atoms in them, the name or the nomenclature is changed a bit. So here we start from the ic, all right, acid. From it, of course, the main the basic name will always be the same. The basic name changes or it will follow the basic name. But when there is on top of that, when there is an addition or subtraction of an oxygen atom from that molecule, the name changes a bit. Like here, if there is ic, which comes from et, right? So if we add one oxygen to that ic, it will be, there is not more than ic, so it will be per ic, per chloric acid. If we remove one hydrogen from that ic, it becomes us, that is hypochlorous. If we remove another oxygen from that, it becomes hypochlorous. From chlorous, then it becomes hypochlorous. In the next example, it becomes, okay, all right. Okay, so it was a chloric acid, HCl3, ClO3 actually, HClO3, it becomes chloric acid, right? And then we added one oxygen atom to this chloric acid and it becomes hyperchloric acid. Per was added to that. When removing, it was added there, when removing one oxygen from that chlorus, it becomes chlorus. When we remove one and then removing another one lands or resulted in hypochlorous acid. And the anions name follows the way the et always will be there. So perchlorate, it coming from perchloric. So this is easy actually to remember. Perchloric, when there are 4 oxygen atom is added or present, we call it perchlorate. When there is no, so it's just chlorate. When there is one less, so it becomes chlorite now, and then from hypochlorous it becomes hypochlorite. Okay, so this is how we should be, I mean, oxo acids are named. And here there is one exercise for you to try I mean, when it was a normal time, but you already have this. So the name is phosphorus acid, right? Phosphorus acid, per iodate ion. Okay, another thing here, from this chlorate, if we remove this chlorine and add one iodine atom here, so it will be per iodate ion, because this is coming from the perchloride. Chlorine is removed, iodine is added, so per iodate ion. Bromic acid, hydrogen sulfate ion, all those things, the name of these. All right, so what about bases? The substance that, in a simple sentence, the simple way definition, that the substance that yields that or gives hydroxyl ion when it dissolves in water. All right, so when it will be dissolved in water, hydroxyl ion will be released. So sodium hydroxide is one. Okay, potassium hydroxide is another one. It will produce a hydroxyl ion as well. All right, and it is clear that it will produce. And then barium carbonate. It will not produce hydroxyl ion, but directly, but indirectly it is one of the bases. Okay, hydrates, when that one compound has some water molecule in it, all right, when one compound has water molecule in it attached to them already inside it, that we cannot see, but of course if we do some testing, we will see that there are some water molecule on top or inside that molecule, and that is why its characteristic or its physical properties changes. So that compounds are called hydrates. For example, magnesium sulfate, it has 7 water molecules, so it's magnesium hydrate, heptahydrate. Always you cannot say, you can say 7 hydrate, but it does not, it is not convenient to say in that is 7 hydrogen or hydrate, but heptahydrate, it follows that Roman nomenclature. Okay, so magnesium sulfate, heptahydrates, and then strontium nitrate, tetrahydrate, and so on, copper sulfate, pentahydrate. And just because of this water molecule inside here, in these compounds, this physical property changes, totally changes. It's not anything like similar. From this photo, we can see that here it is something with that the copper sulfate with the water, and this one is dry, so it does not have any, it's copper sulfate, just copper sulfate. It does not have water molecules attached to them, but here there are water molecules, so the it is very powdery. It is how do you call it, crystal, and the color is also different. Okay, so now we will go more into the periodic table and we'll see some interesting thing, some interesting characteristic of the periodic table as well. So periodic table, where we can look for a chemical compound. Yesterday we are talking a little bit about it, so we'll go in detail into it. Periodic table is a chart or the convenient space for us to understand or to find out the property of a chemical, all right, in a very short time, conveniently. So periodic table, and this, it is not like the periodic table was prepared and then it was somebody put it here in a way, and it is in a very easy way. It was not easy to form the periodic table, and the periodic modern table that was proposed was by Mendeleev. It's not in modern time, it's quite a long time ago actually. So he proposed that one, and since then, and he was a genius, he found out that the elements can be arranged based on their electron number, and when we put there based on their electron number, other properties matches nicely. So he found out that way, and then he started to put that way. So I don't know about you, but when we were in school, we used to know that there were 105 elements in the periodic table, right? We used to learn this way. But nowadays, we can see that there are 108 elements on the periodic table, modern periodic table, more than that actually. Some of them, till today, it is 118 has been proposed. Not all of them has been found yet, or has been found the property yet, but it is not 105 anymore. It's more than 105. But those after 105 was found, they have a very short life. Okay, what is called that short life means it is a very short shelf life it has, so it becomes destroyed very fast itself. Like some of them has a millisecond, small, very small way. So it has to be a very high specific instrument to find out that whether there was some element was produced or not. And from 113, 14, 15, 17, 18, these elements has been named, and they were found, was developed rather than found. It was developed in these places. So based on their developed places, it was named. They were named against the place they were found or developed. Japan, Moscow, Tennessee, and Uri Orgasian or something like that. So when they will be found, they will be named according to their place found them. Once again, yesterday I myself was confused with this table, and actually it is correct. I don't know, my brain tricked me actually. And here, so we know that now already we know that in periodic table we have divided them into three major blocks, right? Three major blocks: S block, D block, and P block element. So when we go from one block to another block, they are, the main difference between them, their valence shell electron or available valence shell. In S block, all of them has their electron in S block. Okay, not necessarily the same S. Someone will have 1s, another will 2s, and then 3s, 4s. As we go down, the number of S, as we go down the periodic table, the number of S increases. Why the number of S increases? Can anybody tell? I cannot see your chat box, but can you tell why the number of, what does it mean when the number of S is increasing? Anybody? The n principal quantum number is increasing, right? From n it goes 1, 2, 3, 4 in that way. So the principal quantum number is increasing. That is why the number of S is increasing. So when it is going down, we say we're going down the group. So now it has been, we can say that this is one group, this is another group. So group 1, group 2, group 3, I mean modern table, group 4, previously it was 3, 4, 5 in that way, 3A, 3B in that way. So 4, 5, 6, and then until 18. 18 groups are in the periodic table, and then the period is this one. This is the period 1, hydrogen the period 1, period 2, okay, period 3, and this way. So period, when we go along the period from left to right, it says that we are going along the period from left to right, and that is why it is shown in this way, the period in this arrow, so that it shows that in the same period the elements are going from left to right. And when it is showing by this, the group, I mean from top to bottom is going down. That means from we are going on the periodic table from top group on the same group from top to the bottom. So that is the thing that has been shown here, and don't get confused with this. This is the period. This is the period, and this is this is the period, and this is the groups. So if somebody says that, okay, one element in group 5, right, in group 5 and period 3, so we cannot have that, we cannot miss, but to find the exact compound or exact element, if it says that group 5 and period, let's say 6, is it 6? 1, 2, 3, 5. 1, 2, 3, 4, 5. Okay, 5. Okay, 5 and 5. So 5 group 5 period. the element is niobium. In that way, we can spot one element. And based on that group, we can also find out what will be the characteristic of the element, or what to expect from that element, or in a chemical chemical properties of that element, or how would it behave if we start to do some reaction in that chemical, or sorry, with that element. Okay. What are the information we can get from here is the atomic radius, melting point. Where is it? Okay, the atomic radius, melting point, electronegativity, and ionization energy. Okay, and atomic radius, of course, if we look, okay, I go to the periodic table where we see a better one. Okay, so this is my favorite periodic table, actually P table from the internet. You can also type P table and it will come up. Okay, so here on this periodic table, there is quite many features. Actually, we can try which one is alkaline metals, alkaline earth metal, and it will highlight that part. So alkaline metal, I hope that you can see. Okay, I'm showing the periodic table now on the internet, I mean, a browser. So I hope that you can see it. So alkaline metals are on the group 1 elements. Alkaline earth is group 2, and so on. Lanthanide, actinide, transition metal, post-transition, non-reactive non-metals, noble gas, metalloids, all those things, it will show up, or it will be highlighted when you move your cursor over them. The thing is, when we start from here, actually hydrogen is okay. Hydrogen is one electron and one neutron is there in that hydrogen atom, and across that point, hydrogen actually shouldn't fit here. That's why there is no other better place for hydrogen to put. So it was put here. But let's not talk about hydrogen. Let's talk about helium, beryllium, all those things. So if lithium, we start from here, lithium 3, that means it has a 3 proton, beryllium has 4, boron 5, 6, 7, 8, 9, 10. In this way, so when we go from left to right in a period, left to right, in the same period, we see that the electron number, the proton number, what is that called? That atomic number is increasing, right? The atomic number of the elements is increasing from 3, 4, 5, 6, 7, 8 in this, and sequentially it is increasing from low to high. Again, same thing goes like 3, period number 3, sodium 11, magnesium 12, aluminum 13. So in this way, it is also increasing when we are going from left to right. And the same trend you will find if we go from the same, period. Okay, same group. So for group 1, hydrogen is 1, lithium 3, 11, 19, 37. So it is increasing. In that way, it is increasing. So when it is increasing, the number of electrons, right? The number of the atomic number is increasing. That means the proton number is increasing. So what we expect is that their size was supposed to increase as well, isn't it? the size of the atom was supposed to increase. We expect that the size of the atom will increase as well, of course, because it has to accommodate 11 electrons and of course proton and neutron. So here it has only 3 for lithium. It has 4, so it has to be bigger in size. The house has to be bigger in size. That is why it's supposed to be, 4 here, and then 5, 6, 7, 8, 9, 10, same thing. And the same, it is logical that it was from lithium. Sodium will be bigger, potassium will be much bigger, and rubidium will be even bigger than that. And so on the same period, fluorine will be bigger than lithium, isn't it? So this is our logic, but there is some problem. There is not always the case that it will not always increase the same way because of some of the properties. Okay, so now let's move to that our lecture slide. But if you are interested, can look at this periodic table. All right, so that the P table, and it is interesting. So atomic radius, we see that. Let me make it a bit bigger. I hope you can see now. Okay, so the atomic radius that we see, it is increasing, or supposed to increase from left to right, all right, and from top to bottom. It is supposed to increase, but it does not increase. It rather reduces the atomic radius, rather it reduces. Melting point is actually, it does not depend on the size, but it depends on some other thing, how the electrons are strongly attached in that element. It depends on that. So the melting point for metals here in the middle of the periodic table, right? In the middle of the periodic table, we know that it is the transition metal area, right? It is a transition metal. So leave out this series, it is unknown still. Okay, so this is the transition metal area, and then of course due to the metallic characteristic and metallic bonding and all those things, it will have high melting point because their bond is harder to break. Okay, even though this is the same, atoms are engaged or attached to each other, to melt them, it will need higher energy, much higher energy. Okay, that is why the melting point for this series transition metal is high, and actinide, lanthanide, actually it also falls in between this here, right? It is here. They're supposed to be here, something like that. So there are some of them melting point is also higher. Electronegativity. For electronegativity, we know that when the energy, the amount of energy released in the process of adding an electron to an atom, yeah, this is the electronegativity. If we bring an electron from far away, let's say this is an atom, it is the nucleus, this is orbital, there are some electrons here already, but we want to add another electron, this is the electron, okay, another electron from far from here and attach it here because it needs. It is not that we forcefully adding it, but sometimes it can be forced, but let's say that it needs, and then this electron is added to this atom. How much energy it will release? Why it will release the energy? Because this electron is required or needed by this atom. All right, it needs to become more towards that towards ideal gas, the noble gas, ideal state. To move to the more ideal state, it will release. It was an excited state, so when it got that what it wanted, it will release some excess energy and becomes more relaxed, more stable, and that is why the energy will be released. However, when we express this electronegativity, it is expressed as positive sign. It is not negative sign. Even though it releases the energy, it is not negative sign. It is positive sign is shown, like 5 kilojoule, not that much, but let's say it's 500 kilojoule. Okay, 500 kilojoule of energy is released, and that the electronegativity is this, and that is the much energy has been released, so that it has a higher electronegativity. So yeah, this is the thing, that is electronegativity. Sorry, I was talking about the electron affinity, not electronegativity. Okay, so how do I delete this thing? Anyway, so this is electron affinity I was talking about, but this is electronegativity. Okay, electron affinity I was talking so far. Electron affinity, but electronegativity is the how much energy it will, or how much it will one atom wants, or the tendency of an atom for getting one electron to be on its orbital. Okay, how strongly does that element desire or want one electron to be in its orbital? That is the electronegativity. And electronegativity is, there is no scale for the electronegativity. Yeah, I mean, it is not measured, the electronegativity, but fluorine is considered the highest, and it considered 3.99 actually. Okay, 3.9 on the electronegativity. There is no unit for electronegativity. All right, 3.99 is considered fluorine, and Linus Pauling, actually, he came out with this idea that we put the electronegativity to the fluorine maximum, because fluorine is the maximum. It wants more than any other elements on the periodic table, one electron. All right, it just wants one electron more than any other element on the periodic table. So that is why the electronegativity for fluorine is the highest, and it is given 4, or precisely 3.99 or something. And yeah, so this is electronegativity in how much it wants it, and all other elements, how much it wants that electron to be its own, is comparing or it's compared with that of fluorine. So fluorine has the highest, then oxygen, then chlorine, and so on, nitrogen, and so on. So as we can see that if we go from left to right, left to right, if we move on the same period, the electronegativity is increasing. Electronegativity is increasing. And again, from diagonally, if we go, we see that electronegativity is increasing even, I mean, in gradually, right? Or from top to bottom, if we go even, we see that electronegativity is increasing higher, more. But if we say that from bottom to top we move and electronegativity is increasing, it does not translate, or it does not convey that thing, because here if we look, it does not increase in that sense. Almost same, this thing, this one, this one, this one, this one is almost same electronegativity. So the best way to express that, if we go from left corner to right corner, the electronegativity will increase higher. Okay. And another thing is ionization energy. Ionization energy is the amount of energy it requires to remove an electron from gaseous atom of an ion. It is, of course, always positive. How much energy would it require to remove one electron when this element is in gaseous state? Of course, they will be very higher because they are already stable and they are noble gas, right? They are noble gas. They do not want to lose any electron, or they do not want to give any electron to anyone. So they are very stable, they are okay. And if you are trying to remove that electron from them, you have to have a very high energy, okay, to remove one electron from them. Fluorine being electronegative, very electronegative, it always want to have the electron. It does not want to shed one electron from it. That is why its electronegativity, ionization energy is very high. And so this is the same trend, is almost similar trend with the electronegativity, that if we move from left to right, or from left corner, left bottom to right top, the ionization energy is increasing in that way. Okay, let's talk about the terms in atomic radius. Radi means radius, okay? Atomic radius, as we said, that here lithium has 3 electrons and then neon has 10 electrons, but atomic radius is decreasing. All right, atomic radius is decreasing. It's counterintuitive. It was supposed to be bigger than lithium. If lithium is this size, neon was supposed to be this size. Why it is happening? Because the number of proton is increasing. Okay, number of proton is increasing, and that is why. Guys, I'm sorry I cannot continue the class today. All right, I have some urgency. So I'll see you on next next class, whenever it is. Please look at the timetable. I'm so sorry that I cannot continue now. I have some urgency. All right. If you have any question, please email me. Okay. Bye bye.